So my name is Ben. I work in Munich on V8. I've been working about 2 years on this VM, and I lead the compiler team. And I'm going to talk a little bit about V8, and I'm going to talk mostly about how V8 and production systems relate to doing research, and kind of give you at least one perspective on that. I've been in and out of research. I went to grad school. I published papers, and I actually enjoy doing research. I'm going to give you a somewhat sarcastic picture of V8. It is actually a really cool system. There's a lot of really cool technology going on inside, a lot of cool optimizations. There's not been a lot of attention from academia, and part of that has been a lack of publication on our side, and also just a general lack of information about how JavaScript VMs work in the literature. This is kind of an example of the divide between academia and industry. And I'm going to give you a bit of a perspective on value systems and why that might be. And also, this wouldn't be a worthwhile talk if there was not some deep technology and cool optimizations presented. And sort of, I'll try to end with some rhetorical questions about where do we go from here. A little bit of background about V8. It was really the first fast JavaScript VM. One of the key ideas was introducing this idea of hidden classes, which are essentially turning JavaScript objects, which are basically hash tables, into things that have a sort of constant time field offset. It was a compile-only VM. There's not very many production VMs that are compile-only, and that means that it basically, to generate code, you have to generate code fast. So the sort of baseline compiler just walks the AST and emits machine code. It launched in Chrome in 2008. It was a major differentiator between Chrome and other browsers. And it was kind of from like 20 to 100x faster than other JavaScript VMs at that time. In 2010, the first optimizing JIT in V8 was designed using type feedback, and that launched in quite a short time. That was a very, very quick effort. And since that time, we've actually built another JIT compiler, which we launched at the beginning of this year. That gave rise to a horse race, so to speak. Pretty much today, you can say that all the 4 major browser vendors are really fast on benchmarks. But there's still quite a lot of performance cliffs, and the performance landscape for JavaScript is still quite uneven. So that means that there's lots of work still to be done. So all of that production work and really running towards getting a fast VM right away has a cost. It has a price. And part of that trade-off is a research potential. And I use the term shippingness in kind of that's not a real English word as far as I know. But that's kind of this idea that favoring things that are products over ideas and doing things that worked in the past as opposed to taking risk on new approaches. That also favors incremental improvements, and it also means that we build fewer platforms and frameworks, which are sort of internal things that make our lives better, whereas we pursue optimizations. It also means that we don't have much time to write papers. And part of shipping these things also means that you can't really go backwards on benchmarks. So once you get to a certain level of performance, you can't go back. That builds up to some architectural debts or technical debt, and that means sometimes the VM is complex and also fragile. And we tend to favor things which fit in with the existing approach, fit in with the existing code. It's easier to either hack on the side or to sort of work around how it is now. The really innovative ideas take a long time to stabilize. They're risky, and they mean that you get bugs coming in from production. And in Chrome, that means coming in from you people, unfortunately. You get crash reports. It also means that new language features we have to be conservative in the face of, so we don't typically do we don't do things that are not necessarily standardized. Despite the perception in academia, resources are still limited. Even at Google, engineers cost money. Interns cost money. Even interns cost more than students. We can't really afford to waste, quote unquote, waste resources on constant exploration of ideas. That means that we time box experiments. That means that we cut things off when they seem like they're not going to be fruitful. It means we have to commit to a direction. We have to pick a direction and commit to it. A bad direction means some cost later, but at least you've committed to something. Also, that means that past solutions, even if they're suboptimal, are less risky. And the other thing about this that I'd like to communicate is that maintenance has a continual cost that you don't see in academic projects. In particular, fixing issues, branching, releases, and dealing with perpetual churn from other software systems, this actually costs engineer time and gives people dark thoughts, like, please kill our project, kill me, something like that. And I think I covered this a bit. Research is sort of an afterthought. At least in V8, we've had the approach of only publishing after we've shipped ideas. So we've sort of proved that they work, and that can take more than a year. And this is only sort of if we still have the interest and still have the drive to publish a paper about that. And this is partly because of this sort of drip of stabilization. Engineers are not rewarded the same way in industry as in academia. It depends exactly where that tuning is on which, maybe if you're in an industrial research lab, it's one way, whereas a product group is a little bit more the other way. And writing a paper takes time. You have to justify that to the management somehow. And of course, there's onslaught of new things coming in. You want to write up an idea that you finished, but there's bugs, there's users asking questions. Usually they're wrong, but they're still asking questions. And there's features coming in, and there's having a life. So I want to share some observations from doing work in production systems and also just doing work in general. I think that, at least in a production system, one really good idea is not enough anymore, especially when performance starts to plateau, which I think it is starting to plateau for JavaScript. An example of that is we have this optimization in V8 where we assume an object gets to a certain representation, and after that it's not going to change anymore. So using this, we can actually elide some type checks. Once you do one type check, you can assume that it's not going to migrate away. So this only gives you a small bit of performance. It's probably not an idea that you could write up and put into a research paper and get published. Maybe it would be a paragraph, a page, 2 pages in a tech report, but that's not a research paper. Another example is how we have techniques for eliding prototype chain checks, which are important in JavaScript. There's a tangle of pointers in the runtime representation of JavaScript classes, of JavaScript types in the VM. And again, that's kind of not quite getting to the paper threshold. So that doesn't really come out as an idea that penetrates into academia. Similarly, for assuming that certain constants, globals are constants. All those are little ideas, but you start to put them together and you start to get the percent after percent after percent improvement. And that's how the engine gets faster. And complex systems need to sort of progress using these small steps. And these don't, even a collection of these little ideas don't really make a good paper. Another observation I have from my experience is that when we do build patterns and frameworks inside of VM, they emerge bottom up. So we get many examples of a particular optimization or a particular pattern on how we structure the code. And then once you see the patterns, then you can actually develop something that actually covers the patterns. I'm going to give some examples and do a deep dive into some technology to show you why I think that this sort of bottom up actually works better. But this is actually unfortunate because those patterns are the most transferable parts. What you learn in one VM, you see many instances, and you sort of collect that into a reusable piece, and that's the piece you want to communicate. And it's hard to get to that level, and it's hard to write papers about those. So these kinds of ideas, they're tough to pitch in a research paper. Actually, I think it's really important to publish research papers of that kind because they are peer-reviewed, and there's sort of this threshold. There is a tech report mechanism, but honestly, tech reports don't get this sort of fanfare that research papers or conference papers do, and they're often ignored. And also, they don't get rewarded in the same way. So I'll talk about a little bit about the flow engine. So this is essentially a framework for doing compiler optimizations in Crankshaft, which is the sort of middle compiler that we launched in 2010. We noticed that you're writing compiler optimizations sort of one instruction at a time. And if you get new people come in that have an idea and they sort of think of it in terms of what's right in front of them, which is the IR, and they will do some very simple instruction at a time thing. Examples are like load store elimination, type check elimination. We can see the flow from one instruction to the next. And you can do very local things. It's really easy to do those. And again, it's incremental because you can add them. You can see a small increase. But then after a while, you want to extend them to work on the whole control flow graph to do data flow analysis. And after a while, you notice that basically these start to actually look like the textbook algorithms. So you read the Muchnick book and it shows you solving all these data flow equations. It's very abstract. It doesn't really necessarily show you how it could be applied to a compiler that you have. You only see that after you see many examples. And so that's one of the things that I did in Crankshaft was develop Flow Engine to solve the data flow equations for you. That wouldn't have made sense to do unless I had at least seen 3 or 4 optimizations that could fit into that. So I'll give you another example of these frameworks appearing bottom up and only after many examples sort of come into play. This is actually a paper that we published at ISMEM this year. This idea, which we call allocation mementos, is a way to dynamically instrument objects and learn about them. So this arises because JavaScript has arrays which you can essentially put anything into. You can delete items out of the middle of an array. You can grow arrays. And so the way those are represented in the VM is different depending on their contents. And depending on which representation you pick, it changes the cost of all those operations. So you sort of want to pick an optimal array representation. That's very related to also picking a good initial size and a growing strategy. And we also noticed after a while that we want to predict object lifetimes. So there's some benchmarks, for example, in some programs in the wild where some objects live a really long time and other objects die very quickly. And if you assume that everything dies quickly, but you're wrong, then the garbage collector actually has to do more work, because typically you would copy once, maybe twice, to promote those objects to the old generation. So I'm going to give you a deep dive into sort of how allocation mementos work and give us the ability as a platform to do all 3 of those optimizations. It's actually very simple. So instead of putting some information directly in the object, we put the information directly after the object in memory. So, and this is optional too. So we can actually have an object that essentially does not know if it's been instrumented, and the instrumentation is added to the end. So we can optionally check for it. And you could think of storing anything that you want into this instrumentation, but for now we'll just look at allocation site. That's basically the place in the code where the object was allocated. And this is an assumption that objects allocated from that site have some of the same properties over and over. So arrays are represented with an indirection in the VM, and they have different representations. So in particular, this example, we have the elements arrays all storing 64-bit double numbers. The allocation site actually records the fact that all the objects from this site so far have only needed to have doubles. But one thing that can happen is that you can actually delete an element of an array in JavaScript, which is horrible. It actually means that you see through that hole to whatever's on the prototype chain. We actually need to sort of set a bit in the map to remember this array actually has holes. So you have to do a second check when you read. So you can allow that check if you know it doesn't have holes. So we actually will use the memento to update the allocation site to be able to show, to be able to remember that objects from this site eventually had holes put in them. Same thing on even more expensive cases if you had doubles and then you added a string or overwrote one of the elements with a string. So this is actually represented differently in memory. We actually will make a copy of the elements. So on a 32-bit platform, those will be 32-bit pointers versus 64-bit doubles. And then we actually have to box the doubles that are there. This is actually a very expensive operation that you want to avoid in the future. So recording a little bit of information in the allocation site helps you sort of skip over that transition step so you sort of start out with a more general representation. So you can also use this platform for doing pretensioning. This is basically getting a signal about how long an object is going to live. So we instrument objects with mementos depending on whether we want to learn about them. And then when the garbage collector runs, it basically collects mementos for surviving objects. And knowing the number of allocated objects from that site, you can compute a rate, a survival rate. And with that, you can sort of trigger, at some threshold, you can trigger pretensioning. And that makes a big difference for the objects, future objects that are allocated from that site will go directly in the old generation and never go through two copies. It also means that we have a chance to...
What's pretensioning?
Pretensioning basically means allocating objects directly in the old generation so that you don't copy them twice if they're living through young generation collections. We can actually learn something and then discard the mementos. That means that we don't pay the overhead for them in the old gen. So we only actually have to use them for a short amount of time. So I want to show you a graph from the paper, not to say how awesome this optimization is, but to say how weird this graph looks. and actually how awesome this graph is. So you see that nothing gets slower. That's the most important thing of this optimization, is that we tuned all of this sort of learning phase so that it's really low overhead. And only when you're really sure that you learned something, then you turn it on, and you get this big speed up. So this is actually very weird from an academic perspective, where you often see charts where some things get slower, some things get faster, and there's some 2 or 3 sentences where they wave their hands and say it's fine. That's not fine for our situation. We rather see graphs like this where nothing gets slower. Also, one thing that doesn't show up that we did present in this paper is that pre-tenuring can make wrong decisions, and you don't want to be stuck with them. So we implemented a backup mechanism that sort of recognizes when something is horribly, horribly wrong, and then backs everything out so that we can relearn. So this does not happen on benchmarks, but this happens in real-world applications, in particular Gmail, for example. It's important. It's long-running. You don't want to get stuck with the wrong optimization decisions. Also, this is, I don't know if you've spotted the bug farm that this created, but you're actually looking at memory after an object in memory. So that if that's trash, then maybe with some low probability it's trash that looks like a memento. And then you start to get confused. It's okay, maybe if you're just using it for a heuristic, it's probably okay. But if you're actually hunting around in that trash memory, something's going to crash. So this is a new system-wide invariant that took quite a long time to find all the places. Nobody had ever thought we would do an optimization like this. So we sort of had to find those and stabilize those. And that's kind of like a more than 1 year stabilization effort, like actually getting crashes from the wild, tracking down the place that's missing, something that needs to overwrite the trash so we don't get confused. And this is kind of a crucible that every V8 engineer kind of goes through. You ship an optimization, everything's great. It took you a week to write the code. It took you a week to do the code review. And it took you 3 months of turning it on, turning it off after you get some crashes from production. Obviously, you can improve that with some testing techniques, but this is always there. I want to give you one more third example, considering I work mostly on compilers. I thought this might be interesting to people who work on compilers. So again, this idea of frameworks and patterns emerging from many instances. And this is how we do optimizations in Turbofan. Most of the optimizations work by doing a kind of local graph reduction. So we use an intermediate representation, which is, we call it the soup of nodes, which is kind of a play on words from the sea of nodes. It's a slightly more relaxed version of the sea of nodes. And most of the optimizations work on this. And actually, we have shipped Turbofan like more than 6 months ago. So this is, again, stuff that's been already in production. So just now all the compiler IR is coming right at you, so I hope you're prepared. It's basically a graph. All the computations are just nodes in the graph. That means constants, parameters, arithmetic, and the edges basically represent dependencies between computation. So they can represent value dependencies. They can represent, as you'll see, effect and control dependencies. And we do SSA renaming, so there's no such thing as a local variable in your code in the graph. Basically, we rewrite the references to local variables with whatever value you actually used assigned to it last. That means the graphs actually are not trees. They're not expression trees like you would see in a textbook. They're actually DAGs, and actually they will have cycles too once you get into having loops. The key idea is that this kind of a representation, it does not dictate an ordering like a control flow graph, which has instructions one by one in order. It constrains an ordering. It basically represents all legal orderings. So basically, illegal orderings are ones where the edges go the wrong way. So we use effect edges to order operations that deal with mutable state, so anything that loads from a mutable memory location or anything that stores. And those effect edges basically make sure that those things stay in the right order that they were specified in the program. So reads and writes have to be ordered with respect to each other. We use control edges to represent control, and these are also dependencies. They all go backwards in time. So you can kind of think of this as end is the most important thing in a function. That's kind of the goal of calling a function, is to get something out. And so end represents where you want to go, and then it just depends on everything you sort of need to compute to get to end. So that can be control, that can be effect, and that can be an actual value, the return value of the function. Okay, so we started doing optimizations on this representation, and it's actually really natural to see these as local kind of pattern matching. You see something which is obviously suboptimal, and you can change it to be something cheaper. So constant folding is an obvious example. Strength reduction is if you're adding 0 to something that's a no-op, or replacing something with a cheaper version of that. And similarly for SSA renaming, phi simplification is basically reducing the complexity of the data flow relation. You can do reassociation on this form too, so it doesn't necessarily have to be one node at a time. The other thing is that Turbofan is designed to compile JavaScript code to machine code, and there's a big gulf in between. And so we use type information as part of that lowering process. And this is actually another instance of how reduction works on the graph. We basically have these static types associated with nodes. Since we know, so we have a node that represents a JavaScript add, which includes all kinds of overloading rules. But knowing the types can actually statically determine what overloads those are, and we can boil the code down to a lower form. This is actually good for code that has latent static types. In particular, there's this ASM.js subset of JavaScript which has a lot of type annotations which basically give you this for free. You can extend the reducer idea to doing common sub-expression elimination. That's redundant computation in the graph. So you have 2 computations of sign. They will eventually look something like this, where you actually have a node that represents the input and then 2 nodes that represent 2 independent signs. You can just collapse them together. And this works even for effectful operations like loads. So if all the dependencies are the same and the operation is the same, it will compute the same value. Okay, so we went even further step along this road in all control reduction, all sort of removing dead branches actually can be expressed in the same way. So if we have a branch that has a condition which is a constant, then we can actually replace that. The one arm of that's not going to be taken with dead, and the other one with the actual sort of assuming taken. And you make more rules, and all of them are local, which is great. And it basically means that you only have to reason about the sort of nodes that you're modifying. And then we put this into an engine, and I'll show you that in a bit, but basically gives us the sort of dead code elimination as a reduction. And the great thing is that you can mix all the reductions together in sort of one sort of pass over the graph. So this is the kind of framework that emerges from this sort of seeing all the local transformations. We do this reduction of the inputs, and then we're at a node, and it's got some edges coming in, and then we are going to apply some rules, and that's going to either produce new nodes, or it's going to rewire the edges to be some of its inputs, or maybe even constants. So there's an ordering problem, and actually you want to do this in a way that's the most efficient, because visiting the graph many times is expensive, so it's compilation time. So we basically realize that you want to do the rules in post order, and the way we implement that is with an iterative reduction. So you can think of starting at end, and you only want to essentially, excuse me, look at the code which end really depends on. You don't look at code that it doesn't depend on, because obviously that would be dead code. So we use an explicit stack for this, where every time we want to go one deeper, we push something onto the stack. And now it's actually really easy to see what the local rules are. You have the node on the top of the stack. If it has any inputs which have not been reduced, then you recurse on them. And finally, you're either going to get to a leaf or you're going to get to a cycle. And when that happens, you apply reduction rules. And you can apply all the reduction rules. And hopefully, if they don't fight with each other, then you actually will get the right result. So this can happen. You can have a cycle, and that's if you would have a loop in the graph. And then there what we do is basically you have to apply some of the rules. You do a partial reduction, and then you sort of allow that node to be popped. And eventually, when you get back to the place where that cycle is completed, then you can re-reduce it. So this computes a fixed point over the reduction rules. I think when we started, so I didn't think that this would be so abstract when I started doing Turbofan. But actually, seeing all these instances, we saw the commonality between them. I just want to give one more anecdote about how shipping this is hard. So we implemented escape analysis in V8 in late 2013 and shipped it, or so we thought, right? There was the main blocker here was bugs and deoptimizer bugs. So that's basically when the sort of optimized code has made an assumption that doesn't hold. You have to go back to unoptimized code. And if you have escape analyzed objects, those have to be essentially materialized. They have to be turned into real heaps, real objects on the heap, and their values put in. Well, there's this language feature in JavaScript where if you have a JavaScript function, you can get the .arguments property. And what that actually does is it walks the stack, it finds the last function activation, reifies the arguments passed to that function at that call site, and gives you an array back. And you can modify that array if you like. That's actually not a language feature. That's not spec'd by ECMA, but that's part of what V8 gives to Chrome, and the web uses that. So there are websites that depend on this. Of course, we knew about this feature. It causes a de-optimization. It's a slow path. That's fine. We're fine punishing those people. But those websites, so it worked fine, but we would actually accidentally materialize 2 copies of the object sometimes. And that's fine if you don't modify them or don't compare them. But actually, they went even a step further where they were modifying the contents of that arguments array and expecting this to work. So we had to do, engineering solution. You have a hash map on the side, which is like you make sure that you only materialize 1 copy of those, and sort of that hash map is, has to be known by the GC and has to be popped off the stack at some point, memory leak and stuff like that. So this is kind of like an idea. You're getting an idea of what the sort of round trip to stable is for a feature. You find something like this, and it's a complex system. And yeah, we could blame this on some horrible language feature, but this is always going to come up when you have a complex system. It could be your own creation, and actually, I would say this is V8's own creation by offering this language feature to Chrome. So I want to kind of bring the technical discussion to an end and talk a little bit about what research in V8 looks like today. So there's things going on. Turbofan is it's kind of my baby. We've got a nice team working on it, a lot of bright people working on how to rephrase optimizations to get the best out of this representation. Turns out to be way more graph theory than I was prepared for. It's somewhat frightening at times to think about the complexity there. But Turbofan also gives us a chance to rethink some architectural ideas that V8 had from the beginning about how it uses type feedback and how aggressively it uses that type feedback. So there's some re-architecting there. There's always a tough task to find an incremental way to do that. And of course, there's compiler optimizations that we're always pursuing. It's hard to say whether or not they're researchy until you see what the actual solution is. So our very own Andreas Rosberg, who is here, is working on strong mode, which is a subset of JavaScript, which is more controlled, and hopefully we'll get the ability to optimize code better with strong mode, and also you can have programs that have a little bit better static guarantee. V8 is a production system. It's hard to build these new features in, so that maybe is harder in V8 than it should be, but that's also part of the challenge. And then along those lines, there's an even further proposal to add static types to the language, which is called SoundScript, which is also Andreas. I'm also involved in another project, which is a collaboration with Mozilla and Microsoft and Apple. It's called WebAssembly. It made the news a couple weeks ago. Maybe you heard about it. But it's essentially a native code format for the web and more. And we hope that it can be much, much more. But there's actually quite a big effort behind this. And I think this will sort of solve some of the problems that web browsers don't really support use cases like compiling C++ games to the web very well. There's actually a lot of ideas that we're exploring in GC in V8. One thing that we do now is that we try to hide GC pauses in between frames. So when you're running some graphics thing, there's some slack time between when you compute what a frame looks like and when you actually show it. And we try to find a way to actually squeeze a small amount of GC work in there, so we hide it from the user, so you don't miss a frame. That actually works really well. You don't change the amount of GC work that you do. It doesn't actually make it more efficient, but it makes it a better experience for people. And that's actually really important. We're also working on a fully concurrent GC, and that's really tough to do in a production system. I think Tony could probably vouch for that. And there's a lot of interesting things going on there. And also we are working on studying object locality and things like that. I think this fell off the end there. this doesn't really fit. So Virgil is my baby language project, which I wanted to plug. That's not really in V8. Maybe Virgil to WebAssembly, and I could claim that it's in V8, but there it is on the slide. So now it's kind of rhetorical question time. Where do we go from here? I don't necessarily expect you guys to answer that. I don't have any particular expectation about what that means for V8. But the question is kind of like, what is the right forum for discussing these secret sauces and all these tricks that are in VMs? I think it's important to share those things. I think it's important that language, that is part of the cultural understanding of how to build VMs. And also, good ideas can be reinforced and bad ideas can be maybe also shown to the light. VM implementers tend to talk shop when we run into each other at conferences like this. I think that's good. But I think there needs to be sort of a literature. There needs to be a paper record about these things. There needs to be places you can go that you can read about how the engine works. That's important for application developers too, to know about how the VM is going to deal with their code. JavaScript VMs are not documented well. Maybe research papers are the right vehicle. I don't know. I like writing research papers personally. I think that's valuable to show something that's on the cutting edge. But also tech reports are probably valuable. Maybe your experience is different. I don't know how many tech reports you people typically read. I think maybe blogging also could be important too. So we will launch a V8 blog here in a week or two, and we'll talk about some more details there. Also, word of mouth probably also works. Interns really work, so we've had a couple of very successful internships, and we're happy to continue those programs. So that's also a way that we can sort of share knowledge by sort of bringing someone into the fold, putting them through the pain of V8, and then sending them back and sort of getting them in the back door to academia. All right, so thanks for your time. Sorry for the whole hiccup situation, but
similarly complex like C2 easier to understand and start working it?
Yeah, I think so. In addition to tech reports and papers, I think design docs, which could be more or less formal, could also help, and maybe implementation guide. Maybe that's what you're looking for, which is like an annotated sort of, here's what you'll find in this file. Here's why this file is separated from this other file. That kind of thing. Those are really important. It's hard for us to find time to do that, and I actually wish that I had more time to do that. But I think that maybe that would be a way forward. Maybe we should hire some people to do technical documentation. I mean, that works at other companies, in other projects. And that's not a joke.
I have a technical question regarding this allocation memento.
Yeah.
So how do you identify the allocation sites? Let's say I have one helper function in my program that does all allocations. Will this helper function, will you take the context, the calling context into account?
So currently we don't take the calling context into account. So I didn't explain a bit about the policy, but our policy is to emit allocation mementos in unoptimized code, and unoptimized code doesn't have any inlining. It basically has an allocation site boiled into the unoptimized code that says this is where it came from. But you could, for example, have a different policy where you take one stack frame into account, and then you find, that means you have more allocation sites because you have more context, right?
Cool, more research areas. Right?
Sorry?
More research areas.
Yeah.
Yeah, just speak out.
Hi, yes. Cliff, I did the Sea of Nodes a long time ago.
We're aware of that.
Just curious, why did you do read after write dependencies?
Repeat the question.
So Cliff asked, why did we do read after write and write after read dependencies? Well, so technically they're all treated the same. And actually our scheduling algorithm treats them all the same, but it doesn't have to. I think we can treat effect edges slightly differently in the scheduler to get better schedules. We can go into it offline, but we basically treat all edges as requiring dominance relationship. Other than splitting, the splitting out also happens in the scheduler, so we will replicate some computations in the scheduler algorithm. We should probably talk.
The better question is, yeah, what level of aliasing information do you have available?
Uh,
I
so
don't know what JavaScript is it all alias?
Yeah, so we have a little bit of alias so the question is, what level of alias information do we have, like to tell different memory locations apart? So in Crankshaft, we have something that's relatively coarse-grained. It's like the offset and the object, and those don't interfere. There's no aliasing relationship where those could be. And then for the actual objects, we can tell two allocations apart and an allocation apart from something that comes in from the outside. So it's not super detailed. We don't do really heavy weight pointer analysis for that.
You showed some node reductions, and you quickly said that sometimes these node reductions could both apply on the same situation. How do you resolve that?
Very
just choose
carefully by hand. So what can happen? In particular, one thing that can happen is that one of these reductions is lowering, so it will take JavaScript and reduce it to something else, whereas another reduction will reduce it to something that's cheaper. So if you are producing a lot of new nodes, there's new opportunities to find common sub-expressions, and so you can sort of get confused. You could potentially, if you had reductions that could cause a cycle, one reduces it one way, one puts it back. We have to be very careful. We don't have any safeguards to well, there is one small safeguard. We don't apply a reduction to the same node twice, the same reduction to the same node twice. We will sort of at least let one other reduction run on it first. So there's some safety fences. It'd be nice to have a theory about that. There's this idea of confluence in programming language reduction, which is like you will, no matter which order you go in, you eventually get to the same result. It'd be cool to have theoretical guarantees about reductions like that, but that's something that, that's a research topic.
C2 had the same problem, and I had the same rough answer. Everything had to go to a canonical form, and you had to either count down nodes or edges to know that we were always going to reduce, but you could still write something that would blow up on you.
Yeah.
A small question. As you tell, you have a requirement that all optimizations that you introduce don't actually give a penalty for existing code. So you shouldn't have regressions on your benchmarks.
Right.
Though you already say that you have optimizations like global value numbering that is known to, in some cases, introduce computations that were not required.
Yes.
So let's say you have a match example and you have several branches, two branches use the expression and the third one doesn't.
Yes, so I know exactly what you're talking about. I alluded to that a bit. So global value numbering actually does introduce redundant computations, right? Because it canonicalizes. Mm-hmm. And what the scheduling algorithm does is we actually will compute whether that is a redundant computation on some path and split it so that it is no longer redundant.
So you have the undoing of global value numbering.
Yes. And that means that the graph that you get after scheduling is different than the one you had coming into scheduling, which is kind of bad. We can run it in a mode where you don't duplicate anything. And that means we actually get a schedule on the side which you can throw away if you wanted to.
But what's your general approach for creating new optimizations? So in most cases, if you have some optimization, it obviously can be a de-optimization in some cases, at least because you can spend more time actually applying it if you measure the compilation time.
Yeah, so that's always, I think in terms of doing local reductions, they're essentially free. More passes over the graph causes your compilation time to slow down. So we try to keep the number of passes down.
So originally C2 did a couple passes like you're talking about with graph reductions, and eventually went to one where we kept back edges and did a completely incremental. And so adding a new optimization would cost no more than the time to execute it, if it ever executed at all. It would never cause other optimizations to run slower for any reason. So it was always free to run the local optimizations like that. So it sounds like you're really close to that already.
Yeah. We actually do very few passes over the graph, and we schedule only once.
The
If you de-optimize, you're leaving the code. You'll go to unoptimized code. Maybe you come in, maybe you recompile, right? So.
Any other questions? If not, let's thank the speaker.
Pretty much today, you can say that all the 4 major browser vendors are really fast on benchmarks. But there's still quite a lot of performance cliffs, and the performance landscape for JavaScript is still quite uneven. So that means that there's lots of work still to be done. So all of that production work and really running towards getting a fast VM right away has a cost. It has a price. And part of that trade-off is a research potential. And I use the term shippingness in kind of a, that's not a real English word as far as I know, but that's kind of this idea that favoring things that are products over ideas and doing things that worked in the past as opposed to taking risk on new approaches. That also favors incremental improvements and also to things that have a sort of constant time field offset. It was a compile-only VM. There's not very many production VMs that are compile-only. And that means that it basically, to generate code, you have to generate code fast. So the sort of baseline compiler just walks the AST and emits machine code. It launched in Chrome in 2008. It was a major differentiator between Chrome and other browsers. And it was kind of from like 20 to 100x faster than other JavaScript VMs at that time. In 2010, the first optimizing JIT in V8 was designed using type feedback, and that launched in quite a short time. That was a very, very quick effort. And since that time, we've actually built another JIT compiler, which we launched at the beginning of this year. That gave rise to a horse race, so to speak. So my name is Ben. I work in Munich on V8. I've been working about 2 years on this VM, and I lead the compiler team. And I'm going to talk a little bit about V8. And I'm going to talk mostly about how V8 and production systems relate to doing research and kind of give you at least one perspective on that. I've been in and out of research. I went to grad school. I published papers, and I actually enjoy doing research. I'm going to give you a somewhat sarcastic picture of V8. It is actually a really cool system. There's a lot of really cool technology going on inside, a lot of cool optimizations. There's not been a lot of attention from academia, and part of that has been a lack of publication on our side, and also just a general lack of information about how JavaScript VMs work in the literature. This is kind of an example of the divide between academia and industry, and I'm going to give you a bit of a perspective on value systems and why that might be. And also, this wouldn't be a worthwhile talk if there was not some deep technology and cool optimizations presented. And sort of, I'll try to end with some rhetorical questions about where do we go from here. A little bit of background about V8. It was really the first fast JavaScript VM. One of the key ideas was introducing this idea of hidden classes, which are essentially turning JavaScript objects, which are basically hash tables, and so means that we build fewer platforms and frameworks, which are sort of internal things that make our lives better, whereas we pursue optimizations. It also means that we don't have much time to write papers. And part of shipping these things also means that you can't really go backwards on benchmarks. So once you get to a certain level of performance, you can't go back. That builds up to some architectural debts or technical debt, and that means sometimes the VM is complex and also fragile. And we tend to favor things which fit in with the existing approach, fit in with the existing code. It's easier to either hack on the side or to sort of work around how it is now. The really innovative ideas take a long time to stabilize. They're risky, and they mean that you get bugs coming in from production. And in Chrome, that means